Welcome. In this session, we'll explore decision-making using supervised learning, also known as machine learning. These are the techniques that are really at the backbone a lot of artificial intelligence that you're hearing about in today's businesses. And that's because we're able to do identifying different customers with it in order to help predict what they're going to be doing next. We can apply this technique. It's also known as classification to understand what to do with new customers, and we can identify opportunities for business analysts and managers, leaders, to be working together in these techniques to actually get the best value out of them. The ghost in the machine. Some would really argue that modern day machine learning is effectively this, and a very interesting perspective from the concept of mind. Are we actually observing intelligence? I think that's what a lot of people are concerned about, Elon Musk among them, that these techniques could lead to some very unusual sort of outcomes for the future. And personally, I think you'll see that we're still in the days of identifying ramen, so I don't know if I see a post-apocalyptic future just yet, but there are indeed some that are concerned about that, and it's for this reason. Who's using machine learning today? Pretty much any large modern company would be using it, but we as consumers are using these things as well when we do simple things such as utilizing an app for driving, when we're purchasing things and we're getting offered for items that are similar to other customers, to our music preferences that are offered up on a lot of services that are available now more and more worldwide. Large industrial companies are using these things to make their operations better, do predictive maintenance. All those kinds of things are applications for machine learning. These are some cutting-edge examples. I won't spend our video time going into the actual video, but I encourage you to do that. These techniques are evolving very quickly, and while some might read these and sort of think this is sort of silly, you can sort of you have to take a step back and try to really appreciate what the machines are actually able to intuit. So in this video, if you choose to watch it, you'll see a solution that can actually predict with a high degree of reliability the ingredients that went into creating a final dish that is something that's to be eaten, and can actually, from a simple photo, actually predict with very good reliability the ingredients that went in. Here we have machine learning being used to identify ramen that comes from different shops. Now, I think we're at a level where, as much as I like ramen as anyone, it would probably be a challenge for me to distinguish one set of ramen between one set of ramen and another, and then certainly what shop actually made it. But the machines are the point is that the machines are becoming quite sophisticated at understanding novel kinds of stimuli, of imagery, and being able to predict with a high degree of reliability what the actual correct outcome is. And that indeed is making this sort of cutting edge. Another example very recently shared were some advances where Google's DeepMind, which is their artificial intelligence, many of the big companies have these. You might have heard about IBM Watson being another one. But research that was just published on how a computer is able to see an environment from one direction and then intuit or anticipate what the environment would look like from other previously unobserved perspectives. And an application might be something like driverless cars, but again, when you're looking at how a lot of video is being analyzed now for different techniques, it is advances like this that give us promise that that kind of analysis will be very useful and also very accurate in pretty much any application that we're going to be seeking to get out of it. But those are some cutting edge things you can read about. It doesn't just stop with the visual realm. We have audible kinds of solutions that are really novel, using very complex data and being able to anticipate and deliver on outcomes. So very recently, you may follow this example where Google's AI was able to actually place an appointment for a hair appointment for a customer and the patrons, or the owners rather, at the shop actually believe they're talking with a real person. So I encourage you to, on your own time, go ahead and look at this. Another example, the computer actually makes a reservation at a restaurant that doesn't actually take reservations, and the machine was able to pivot in the middle of the phone call and actually understand that, and basically just ask some general questions about when they were open. So very sophisticated behavior that has previously been unseen. So our friend George Box has said essentially all models are wrong, but some are useful. And the machine learning models are no different. They're not exactly correct. There's going to be times that they are in fact incorrect and predict incorrectly, but that's because they're a simplified view of reality, and sometimes these simplified views can help us do really powerful things. So right now we're using these kind of predictions to anticipate when a customer will churn, that is to leave us to go to a competitor, or maybe what the risk is of serving a new customer. So these are really some important understandings that while some of these models could be wrong, they're also very useful. I like to think about what machine learning is doing for us in the way that when we go to a market, the fruits and vegetables have already been grouped for us, such that I know that when I shop out of this basket, they're definitely, whatever I'm getting out of this basket is definitely more similar to what's ever in that basket and different from what's in the basket next to it. And that helps me make a meal, because I might need different ingredients from all of these. You can imagine what a morass this would be if all of these fruits and vegetables were just all in a pile to be able to make a meal. We can't operate that way. There's a great value and utility in knowing that there's an order, and that I know I can treat these ingredients separately in my recipe and different than what I would do with these ingredients. It's very useful. And that is very similar to the kinds of questions that companies are asking. How can we know if a new customer is likely a top customer, a best customer, a customer that I want to treat differently, I want to effectively use a different recipe with, if I know that they are a certain type of customer? And which services would we offer them? And they especially want to know that when they are presented with new customers they haven't seen, just like in this illustration, new ingredients. Where do these ingredients best fit among the set of ingredients that I already know something about? That's going to help me use these appropriately, knowing that something's a fruit, something's a vegetable, something's a root. That's going to help me understand best how to utilize it in my ingredients for the recipe, much like a business would for customers. When we look at the banking industry, we understand intuitively that the higher profitable customers are those that have a really high balance, but also will pay it off, that are low risk. If I have a lot of customers that have high balances but don't pay them off, I'm going to be losing money. I can't have very many customers like this, if at all, in my data. And indeed, I may have other segments of customers throughout that I'm serving, but I want to serve different products and services to customers that might have a low loan balance, for example, that pay it off. These are relatively, maybe high risk, where they're carrying more of a balance, but they're not paying the loan back, and that could be risky to my business. So my best customers are really in this area. And I would consider these my top customers, my very best customers, customers that if I could grow them, they would not just be any old customers to me. They're going to be my star customers. Those are my best customers. And we'll treat these customers with different products and services because they're just in different segments. But I really want to grow this segment here of star customers. So intuitively, we can understand that that's the way their business works. But in real life, the customers are not already laid out in these nice segments as we have it here. It looks something more like this. They're just all sort of mixed up together. And I have to begin to reflect on what the behaviors are of these customers and their attitudes. And then from that, I might be able to create some segmentation strategy that's going to help me understand my top customers and then treat them better. Machine learning is one of the ways that we can sort that out, and specifically the technique of classification is going to help us do that with machine learning. Machine learning starts with us selecting a set of attributes. And attributes could be very simple things like in a banking situation, it might be balance transfer, or maybe the amount that they earn every year, or maybe their marital status, because I know that married people they need different sort of loans and services than maybe people who are unmarried, perhaps. And from that, there's some kind of a pattern where if I knew that there was a certain threshold in terms of the balance that they needed, the amount of loan or the amount of income that they had, there's a threshold that's a tipping point where if I just identify what that threshold is, I might always be able to see who my top customers were. And people without those kind of attributes, well, they might be important to me for other reasons, but they're not my top customers. And that's indeed what the technique is doing with machine learning. It's identifying a set of thresholds. We're going to call those attributes. And if I knew what those attributes were and the appropriate threshold was, I would be able to make a business decision, which is basically just going to be sorting out yes or no. And if I can answer yes across all three of those attributes, I'm definitely likely to find top customers. That's going to be the technique. And people who I can't answer that to, they're probably not going to be my top customer. It might still be important, but they're not a top customer. This is what the technique does. When we think about attributes such as balance transfer or marital status or income level, it's really starting out as what we call a node in this technique. We're actually going to be building a tree, a set of decision trees effectively that help us understand machine learning. So any one of these could be an attribute that the model begins with. So it may be something like balance transfer. And I want to find what the threshold is that I can answer yes. All my top customers have a certain tipping point of a balance transfer that if I knew what that limit was, I would be able to say they're a top customer. Now, once I do that, I'll be forming branches. And so in this example here, I have a branch with two directions here for yes or no that have come off of the main attribute node. Going on that a little bit further, they call it a tree, or we call it a tree, because these build on each other. If I'm not done sorting once I have my initial attribute, in that case it might be balance transfer, I have to continue to ask other questions of other attributes, and I continue to also set thresholds before I can really get down to the very bottom, which would be the final classification. So we use this sort of nomenclature that the first attribute that I enter in, that's my parent node. Every time I come off with a decision that about a threshold, that forms a branch, yes or no. It's met a threshold, it's met a balance transfer level, or it's not. And these are going to be child nodes. That is, after the initial parent node, I have additional nodes that fall under them. Those are our child nodes. And the branches continue on until we terminate at a leaf, just like a tree does. So that's sort of the analogy here. We would, in this example, have successfully identified top customers and then other customers that are not top customers using this sort of classification tree. Now, this method is really known as data mining, where we're at first identifying these attributes. They also use the term feature vectors to define what they are, and we need certain knowledge about our customers to even begin that process. So in the prior example, it was knowing that balance transfer and income, for example, were really important ones. Now we're going to build our model. This is known as induction, or starting with learning. And we're going to do that by testing a combination of those attributes and the appropriate cutoffs or thresholds, we'll call those as ranges, to identify the classes as purely as possible. So what we want at the end is to have this sorted out so that it doesn't look like this anymore, but I have a group, a segment that's very, very pure of top customers and non-top customers. This is effectively a set of business rules. So think of it very much as just a business decision. Yeah, they've met this balance transfer level or they haven't. Now, we have to do something once we set all this up as known as training the model. We're going to be training the model based on data that we already have in our business about these customers. That's what makes this technique so powerful. We're not guessing. We're using the data that we already know about our customers to actually train the best, effectively, decision tree we can, which is going to help us determine the effectiveness of the model by testing it on, again, data that we have. And I'm going to show you that. Once we've trained the model and tested it, then we can deploy it. And we can use it on naive data that we haven't seen before, much as my tomato pepper has shown up in the prior slide that we've never noticed in the past, and we would be able to somehow anticipate the kind of customer they're going to be based on those attributes. Now, we call these top-down, or the method I'm going to illustrate because it's simple to illustrate, top-down recursive approaches to this decision tree. And the logic goes something like this. If after a split, so we have an attribute and we've split it based on some kind of decision, the records are all the same, they're all one class, we can stop and we'll be at a leaf. If, however, after the split, the record has more than one class, then we're not done yet. We have to use a different attribute to split the data into smaller subsets. So I'll be illustrating this idea in just a moment. And then we're just going to recursively keep doing that until we're all out of sorting as best we can, as pure as possible. The method that I'll be illustrating is this CART, classification regression tree. There are other methods, though, that could be used, such as ID3 or C4.5. All of these are very similar kinds of techniques. They're just going to be using slightly different ways of measuring purity at each split and evaluating which cases, which customers, if you will, go into which bucket. That's how they differ, but they all are pretty much accomplishing the same thing. And so instead of worrying about the nitty-ditty details, which is something usually that we're going to be using a computer package for anyway, I think it's important to just focus on the CART and understand conceptually how this is working. So let's start. In practice now, we know that in the end, it's actually not going to be perfect. We have a model where we want to identify our top customers, but it's probably better to think of it as a mix and use the idea of probability to help us. In the end, we're typically going to end up with a model that helps us in an important but not perfect way, just as George Box has told us. All models are wrong, but some are useful. This could be useful. It's wrong in that it's not entirely pure. Either of these cases have, in this case, I have some top customers that have been identified as not top customers. This is just the reality of it. So reflecting back on our use of probability in this course anyway, the sort looks something like this in the end, and that's okay. Now, what do we start with? We, as a bank, might have all kinds of different attributes that we know about our customers, such as balance transfer is just another way of saying the amount that they're loaning from us. Maybe they're bringing in some debt from another bank, another credit card. If you understand how credit cards work in countries that have those, you'll be able to transfer that debt, effectively get a loan. So it's basically like a loan amount. Or are they a loyalty member? Or are they married? Or what sex they are? Are they employed? These are different things that I would probably know about my customers. And you can imagine there's a lot of these. But we have to start somewhere. So let's choose 3. And the 3 that I'm going to initially start with, because I believe that it's important to understand our customers in these ways, especially our top customers, would be the balance transfer, the marital status, and income. And so I'm going to illustrate what we would do if we began with those 3 attributes and just those 3 attributes. The model would begin by us getting all of the data together on a set of customers. Now, where does this data come from? It's our own customers. So they probably had to sign up for some kind of a loan with us, or they have some kind of a service, and they've been telling us what their marital status is, what their income is, and how much money they're asking to loan from us. Balance transfer is what we're calling it here. And we would know across all of our customers how they are. Are they already a top customer, which this person is, or some are not? And it's important to have a mix of these customers in my, what I'm going to call training data, to initially evaluate. It's training the model because we're actually going to be learning about the pattern that fits this model first before we test it. And we're going to be doing that on a holdout data set, which is also known as our test data set. These are the same data. In fact, this all probably came from the same database that I had in my business, but I'm actually going to be splitting the data. And there's different ways to do this. You can hold out 1/3 of the data. You can take the square root of the number of cases that you have. Other packages will hold as much as 50% of the data out. You set the standard with your data scientist as you're actually working through this with your analyst and decide how much data to hold out. But the idea is that once we run it through the model, we'll actually get a prediction on whether or not they are a top customer. And this is what we're after. This is the key idea of machine learning, that once we train a model, the machine, the computer, will then be able to use this, validated on this, to help us understand a predicted class. And we're going to test it first on this holdout data because we already know the answer to whether or not they're a top customer, which is represented here. We will not know that in the future, which is why we have to first train it, make sure that it's tested, that we like the results of the model before we go in and deploy it on future data. So the process begins like this. My first step in this is to look at whether or not my customers have a balance transfer that's greater than $5,000. And I can see in my sample, I have 3 customers that do have a balance transfer above $5,000, which is the threshold that I set of this attribute balance transfer. And what do you notice right away? Every time that I see that there's a balance transfer greater than $5,000, are they a top customer? No, no, and no. Well, that's really valuable information, because every time that there are a balance transfer of greater than $5,000, I can now begin to sort out that every time that they do, they're not a top customer. Now, what if they do not have a balance transfer of greater than $5,000? Do I know? No, I don't. I see a mix of customers that are not yet sorted out as not being a top customer. No, no here, yes, no here, yes, no here, and yes. So I'm not done. I have to pick something other than balance transfer to help us sort out the remaining customers. And so let's do that. Let's see whether or not they're married. Now, as soon as I pick this attribute, married, this is the second feature vector or attribute that I'm looking at, I've already classified these first 3 customers. They're already identified as not a top customer, and I'm not going to pay any attention to them any longer. So they're effectively classified, so I'm done with them. My attention turns to the attribute of married, and I can see here married, married, and married. I have 3 customers again that are married. And so I'm now asking, every time I see if they're married, does it help me know whether or not they are a top customer? Well, indeed, it does. Every time that a customer is married, I also know that they're not a top customer. And I know that because they're my current customers. And so I can continue on because I'm not done yet, but I have classified now a set of customers that are married. I go to my next attribute, which is income. Now my question is, and the threshold that I set is an income of less than $80,000 a year. Every time I see an income of less than $80,000 a year, I'm going to pay attention to them. Well, I only see 1 customer in this data set that has that. And does it help me understand them? Indeed, it does. Every time that they have an income that's less than $80,000 a year, they are not a top customer. So they would get sorted out right here. How about the rest? Can I look and see if I see a pattern with the rest that are remaining? Oh my, I do. And this is good news. Every time now I see I am remaining with just my top customers. Every time that they have an income level that was, well, not less than 80, or in other words, greater than 80, right here, 95, 86, and 90, they were a top customer. So I've actually sorted now all my customers in this data set into one of these buckets just using simple yes or no logic. And that's effectively what machine learning is doing. My trained model has now told me if the balance transfer is less than $5,000 and the customer is unmarried, either single or divorced, and they earn more than $80,000 a year, they are a top customer for me. That's exactly the kind of logic that's going on in the machine. Now, we're excited about that, and that's good news. But you understand that, or it's important to understand, that if the model attributes were entered in a different order, it would also sort out and fit the data. So it's not so imperative to understand the order in this technique. It just means that it was effective at sorting the customers out. And while I'm not going to walk this through, you can see that if you had this order, it would still have produced the same result of sorting out top customers and not top customers. So the order isn't so important, at least in this technique. Now, this classification has now produced for us a set of parent and child nodes, and that was done on those testing points, those split positions, those thresholds that we set at each of the attributes. And that produced for us a set of branches, which were effectively decisions made. Yes, no. Balance transfer above 5,000, no. Yes, whatever it was. Then when we produced a bunch of leaves, we had 4 leaves in that prior model, which is no further tests were needed. We were able to fully understand the customers as purely as possible, and we stopped. So this is basically the process that we just went through. It's important to reflect that these models work really well with different types of data. So whether the data is ordinal, high, medium, and low, strong to weak, whether it's categorical, such as sex, the color of things, different religions, would all be able to work with this technique. And, of course, interval and ratio, times, weight, length, they all work equally well. And we can build these kind of models just setting the threshold for any of these data and be able to test at that threshold and make that sort of decision. Now, these different data can also be split up in multi-ways. So I've been illustrating just dichotomy of yes, no, but you could have a model that sets things up this way, classifying student, working, retired, or small, medium, large. All of these are possibilities. We can also take something that's a ratio or interval scale and break it up into different groupings such as this, and the technique would work equally well with any of these things, but also reflect all of the different kinds of decisions that an analyst or somebody from the business would need to make. That definitely has an impact on the model depending on the direction that you're going to be going with any of these. So you can see why, you know, data analysts are making a lot of money nowadays for making these models, because it makes a big difference how you split these things out. And you can imagine the different combinations of things on looking at this, trying to understand our customers. Classification model building, when we do this at each of those nodes, at each of the attributes, we need a measure of purity of success effectively at each step. And for the CART method, we use the Gini index. There are other methods though, like entropy or information gain, but all of these really are just trying to help us understand impurity. And so I'm going to illustrate the Gini index, but understand that there are other methods. And if you had used a different method that I had shown previously, you might see that the package is going to measure the effectiveness using another type of measure, and that's fine. At each split, though, we're basically asking this kind of question. How certain are you that the predicted class, whatever has just been sorted, is pure? And we are obviously shooting for 100% certain. That would be very, very good. But most of the time we have some percentage of uncertainty because it's mixed. Let me illustrate this for you with an example. Here we have selected 12 customers. 6 of them are top customers and 6 of them are not top customers. We see that right here. And I'm going to say top customers are our stars right here. And we have a parent node, which is the first step of our sorting on asking their marital status. So are they married, yes or no? And perhaps we find out that when the machine has run, when it answers yes, we have this kind of an outcome where 5 of our not top customers were sorted as into this class, if you will, this bucket. But it actually grabbed 2 of our top customers along with our not top customers also in this class. Now, if it answered no for being a potential top customer, we had this sort showing us 4 top customers, which is great, but it still grabbed 1 not top customer. So this is really very commonly seen in these analyses, and the Gini index would actually help us measure that. So here you might notice that the Gini index was 0.5, and now I'm going to show you what the Gini index would be with this situation. In the childhood node of yes, right here, yes, I can see that I had 5 not top customers and 2 top customers. And that's going to create a Gini index of 0.194. On this side, we have 4 top customers and 1 top customer, and that would produce a Gini index of 0.528. Now, just reflecting on this, it's a measure of purity, and we want low values to help us indicate that there's more purity effectively in there. And here, this Gini is very low relative to this Gini because there's more sorted here. We have more cases, if you will, that have been identified in this sort, in this class, and that's why it's getting a lower Gini. Even though, you know, this is also very good. It's identified 4, but it's only put 5 altogether in the overall sort, and so the Gini index is reflecting that it's less pure because the greater percentage, by a percentage, is not top, which is giving us the mix there. Let me show you the actual calculation of the Gini so that we can understand that. Looking at the Gini index on the yes node, which is this side right here, you would take 1 minus 5 out of 6. Where did the 5 out of 6 come from? There are 5 not top from the original 6 top, all in this node, and we're going to square that value. And in the second part, there's 2 out of 6. What are the 2? There are 2 of the original 6 top customers over here, and we're going to square that value. That's what's generating the 0.194. To contrast that on the no node, you can see same thing, same logic's going on here. 1 out of the 6 was classified as from the not top, 4 out of the 6 here, which is very good. But when you do the math, we actually have a higher Gini, meaning we're less certain about the purity. Now, all's not lost. We get to actually average this at this level of the decision tree, and you can see if you average those two together, we actually have improved things from this situation by quite a lot. So if you look at that, this just one decision on whether or not they're married, and it ended up with this sort of a result where I'm going to be treating all of these as potential top customers and all of these as non-top customers, I've definitely improved matters, and that's why the Gini index has reduced. So this is goodness. I would say this has done a pretty good job. Now, as I mentioned before, there's a number of different ways that we can split the data. We've been looking at pretty simple examples of just 2 ways, but what if we have a multi-way split? Well, good news is we can still use the Gini to help us understand the purity of the model. So I'll give you an example where we split the data. This time it's on whether or not the customers drive a car, truck, or motorcycle. And it's showing you whether they are a top or a not top. And pay attention to the Gini index as I look at these other examples. What if I had sorted the data, well, let me back up just one. What if I had sorted the data this way between cars versus trucks and motorcycle ownership, or truck and car and motorcycle together? Now I can see my Ginis are different depending on the splits. This is the importance of the model building step, where the data analyst and the management need to understand, are you going to distinctly treat customers in each segment differently? If so, then this is maybe a good model to go with. If you're not, though, and you're only going to be treating customers with cars versus trucks and motorcycles differently, perhaps this model is better. Or then again, maybe you are focusing on trucks and you don't care so much about customers that have cars and motorcycles. So maybe this is okay, even though the Gini index shows you this had the worst outcome in terms of uncertainty. It would all really depend on the business. Let me illustrate this in a second example here with incomes. So if I had incomes sorted in these buckets, well, what if I changed the income buckets and I wanted to look at them grouped similarly to the above? Well, you can see the Gini index could also be different for them. So I would again have to have a business decision about whether it made sense to go for the Gini that was the lowest. But indeed, that is the one that gives us the most purity. And then one more example. There's nothing that says that these are the appropriate bounds that I would be splitting that data up. What if I looked at a comparison of all my customers that were less than or equal to earning $60,000 a year versus those that were earning more? Well, you can see again, you'd have to make that decision at that node being split and decide what is the best threshold that you'd have to set. In this case, it's saying this is the one that produces the purest split, split around less than or equal or 80 than greater than 80, which is in fact the one that I used in the example. But you can see I could have used another example and that would have produced a slightly different outcome than maybe the one that we walked through in terms of how pure the customers were being divided up. My point is that this gets rather complicated, and it should probably be done in concert with the business, because the analyst isn't going to be able to necessarily always make the best decision, or the analyst would more likely be shooting for decisions that have the most purity. But that might not make the most sense for your business if your business is understanding things that are like this, and you want to know people earning less than $100,000 a year and those earning more. And this model is really going to be the better solution for you. And that's a decision that you're going to have to make within the model to split the data that way. So the goal is to ultimately be classifying previously unseen records, previously unseen customers into a class. And so that's really an important thing to not lose sight of. Everything we've been talking up to this point is basically just helping us evaluate the model building. What about identifying new customers? Well, for that, we're going to need to look at the classification accuracy and the confusion matrix. These are the two ways that we're going to measure the results. So here we go. Remember that holdout data that we started the example with? Well, it's still just been sitting there waiting for us to pick it up. And in this example, I've done that. I've taken the holdout data, which are these cases, these 5 cases in this case, and I actually ran it through the model. Now you remember, we knew whether they were top customers or not because we started out splitting the data and just holding this back. So we knew the same information that we had as our training data that we had run earlier. And this is what the model actually ended up predicting for them. You can see I had 4 no's and 1 yeses. Well, that doesn't exactly match, does it? This really is a top customer, but my model predicted they were not. Oh, that's not so good. Here they are not a top customer, and my model said they're not. Well, that's good. Here they are a top customer. My model said no. Oh, this one is not a top customer. My model said no. That's good. And this one is a top customer. My model said the top customer is there. So that's good. Well, reflecting back on something else we've looked at in this class, it probably reminds you of this sort of an idea where we might have a set of correct decisions and a set of incorrect decisions. And we could go ahead and just do a ratio of that, but it misses the idea of false positives and negatives, which is related to type 1 and type 2 errors. You might remember that we looked at some of this with chi-square tests and other kinds of tests to look at whether or not something was really, in fact, aligned with the group that they were really in. And that's a similar kind of logic here. So it's not, it should be more than just a matter of looking at number of correct by incorrect, 3 divided by 2. We need to look at this idea of type 1 and type 2 error. So for that, we need what's called in this literature a confusion matrix. But it should sound familiar because it is the same kind of idea that we looked at previously. When in fact they really are a top customer and my model says they're a top customer, that's a true positive. When they really are not a top customer and I have predicted that they're not, that's a true negative. So that's goodness right here on the corners. The problem is on either of these situations, they're not a top customer and I predicted that they were. Well, that's a false positive or a type 1 error. Or in this situation, they are a top customer, but I missed the opportunity calling them so, not a top customer. So they're a type 2 error. That's a false negative. So we have this sort of problem on the alternate diagonal that we want to try to avoid. False negatives are sitting right here in our model. This is what it actually looks like when you count up the results of the model, and this is really the problematic here. We have some false negatives. We've created some type 2 errors. We had the opportunity to treat these customers as top, but my model is going to predict that they're not. I'm going to miss treating them as a top customer. How much that matters, it's really a business decision. A false positive can be really a nightmare depending on your situation, because maybe it was really important to know that they're a top customer. You can imagine certainly in medical situations having this situation of either a false positive or a false negative can be really consequential to people's lives. You're either telling somebody that they're sick, that they're not, or probably worse in a medical situation, you've missed telling somebody that they're sick, and they really are. And that's sort of the situation that we're illustrating here with the top customers being misidentified. So what the cost of that is, it really is going to be depending on the situation that you're in, and it's a business decision on that. But false negatives are missing an opportunity is way worse for those kind of healthcare models. So going back to our situation here, we have different models. I think we initially started with this being the actual situation where we have 100 top customers and 900 not top. But we built different models, and depending on the model that we were looking at, it made different predictions for us. So this is in fact maybe the truth, but this model has correctly identified 850 not top and 50 top customers, which is very good. But perhaps this is better, 20 top and 870 not top, or this is better, maybe 40 and 820. The point is that you would really need to understand the business to understand the cost of this, because there's consequences on the alternative axes that there's errors. What you'd be doing here is you have actually got 50 not top customers that you're going to be spending money treating them as top customers. And that's going to be maybe problematic or expensive for you to do. So if you did retain this model, you basically have to decide what's it worth, mistreating these 50 people as top customers. It's also important to reflect on what's it worth, the fact that you have 50 top customers that you're missing, treating as not top. You're basically not reaching out to them. You're not developing any product or service, and you're not doing marketing to them. So that's going to be a business decision on how costly that is. Now, in this simple example, we started with just a few attributes and we chose 3. This is just a number of different attributes that you may have available about either employees or customers or all kinds of different things. It's to illustrate that this list is never ending, and it's going to have a big impact on the kinds of data that you seek, data that you gather, data that you store and utilize about your customers. So it's really important to reflect on the kinds of data that you're going to need, and that is a hypothesis-driven practice that needs to be a business decision really done with the analyst, and not that you're just going and seeking out any old different kind of combination of things, because I think it's a fool's errand and you'll also end up with results that might not be very actionable. Now, a couple of more caveats and cautions. We have to be aware of the idea of overfitting and underfitting. Overfitting is getting a model that's so accurate that it's very good for classifying and understanding the data that I have, but then it's failing to actually predict reality when we see new cases, and that's really a problem. It can happen when the model becomes really overly complex. It can also happen when I just throw in a bunch of irrelevant attributes, as I had shared with you in the slide before, just willy-nilly choosing different variables to put in, different feature vectors to look at. So we also want to avoid underfitting. This is where you have a low quality model because it doesn't predict really well. It could be because you have too few observations or missing data or outliers, and both of these are problematic. Let me show you why. This is a real example looking at the magnitude of earthquakes that have occurred over a long period of time that we've been following earthquakes, and this is their frequency. And this is actual data that have been collected and observed of earthquakes. And this data had been looked at in Japan when they were building the Fukushima nuclear power plant, among other power plants there. And what they noticed was that as they were trying to understand the data, they trained a model that fit the test data. Remember how important the test data are. I'm sampling, predicting the magnitude of earthquakes almost perfectly. And they were able to fully account for all the observed earthquakes. And in fact, they were rather excited about that because you might see there's this bend in the data, which was pretty unusual. So you might remember our discussion on linear regression. A linear relationship, which you could argue if you only had this view of the data, you'd have to definitely argue that it's linear. But then something unusual happens. Well, this is what really captured their attention. They actually overfit a model that predicted one earthquake of magnitude 9 every 13,000 years, and that's because of the bend in the data. They didn't want to continue to fit a data out here where there are no observations, which you could sort of understand why they may not want to do that. We've never seen earthquakes of this huge magnitude and out on a linear progression of the line, and so they fit the line to this data. And as a consequence, they built the nuclear power plant to withstand a magnitude 8.6, which is right over this range here. And that would also have a tsunami of no bigger than about 5.7 meters, which is a huge wave already. And so they thought that that was sufficient. Well, we all know the rest of the story. This little change where they could have, maybe should have, continued on the linear trend, there is a huge difference in this. By overfitting the line, they actually missed predicting a difference of an occurrence by over 12,000 years. In other words, the prediction, which is here, one earthquake of this size, magnitude 9, should occur every 300 years, which is 70 times more frequently than the model that they actually used. Well, you can see where we're going with this. And in 2009, they actually did observe an actual earthquake of magnitude 9, which is 2.5 times more powerful than the 8.6. And they had a 14-meter wave, which is more than double what they had planned for those seawalls to accommodate. And obviously we know it was a huge disaster. So this is an example of perhaps overfitting the data to meet what was observed rather than going with the actual trend in the model. And that could be a real consequence about overfitting. Now, underfitting is also poor. Underfitting, we know when we have any kind of curvilinear relationship and we're just going ahead and going with a linear line, we could also miss something. These underfit models have low complexity but high bias because we're actually adding error in the model by predicting a straight line for everyone, when in fact the data are away from that. On the contrast to that, these overfit models are really highly complex. I mean, you can imagine fitting some kind of quadratic equation or something, to this kind of model. Although it has, very low bias because there's very little error. It's not missing any points. And it has high variance because it's going back and forth, back and forth. It's not a very linear line such as this. And that's really the idea, is that the right answer is probably somewhere in the middle. There's going to be challenges with missing important details by underfitting the model, but we can see the consequences of an overfit model as well for predicting the future. When we do the actual model fitting, there is a way of looking at how well our training data is by the number of nodes that we have in the model to reduce the error. And when we throw our test data in and actually validate it, if we see an increase in errors in the test data as it's going through nodes in the model, number of steps in the model, that could be the sign that we have an overfit model. So we want to watch for this disparity between the errors in the training versus the test. That's one way that we can know, and we can ask for some statistics out of the model to tell us that this is happening. This is a lift chart. That is another way of looking at that data. This is a random guess of the relationship between what we should be seeing in the population and our target as we're running the model. And the red line would be an ideal model that obviously predicts everything just perfect, which we know is never really the case. And our model should fall somewhere in between that. And depending on where it is, you can compare different models. And if you're getting maybe overfit, it's going to more closely approach the red line. An underfit model might closely approach maybe the blue, and we're looking for something in the middle as we're comparing our models. Again, this is why the analysts are getting paid so much money right now and in such high demand for businesses that are doing these kinds of things. So what's our takeaway for today? Machine learning is an effective way to ask these kind of what-if questions about new customers showing up, new behaviors that we want to anticipate, and then actually build products or services that are appropriate for. We've all experienced this if you are using some kind of online businesses especially, and they say customers like you have also bought, or any kind of logic like that. There's probably machine learning that's running in the background. Companies use these tactics to anticipate how customers with similar kinds of backgrounds or activities will approach new products and services that they have. And you really do need deep knowledge of the business to have an appropriate model. Otherwise, you could have an underfit or an overfit model. So it's not an activity that an analyst should be doing separate from the business.